So what we have here is a pair of connected particles that are strung over a pulley. So we need to take in some facts about the question. We've got two particles A and B, respective masses 3 kilograms and m kilograms. We have a light inextensible string, which means the string cannot stretch. However, it can squish up. The two particles can move closer to each other, but they cannot move any further apart. We have a smooth pulley, meaning there's no friction at the pulley. You won't be asked to deal with friction at the pulley. So it'll always be a smooth pulley for your A-level course. The two particles are held at rest, and they're both 1.28 meters above a horizontal floor, and the portions of the strings not in contact with the pulley are vertical, which is, again, pretty standard for a pulley question for the A-level. The system, which is the whole thing, the A, the B, the pulley, it's called a system. And it will be released from rest with B accelerating towards the floor at 1.9 meters per second squared, and A will never touch P. So the first thing we're going to want to do here is add in our forces. Okay, always the first step whenever we're dealing with a mechanics question like this. And so the first ones I'm going to add in are the weights of A and B, which I'm just going to draw in here with a solid line. And then I'll write down what those weights actually are. So for A, we have 3 kilograms. So its weight is 3 g newtons. So we have a force of 3 g newtons heading down that way. For B, its mass is m. So we've got a force, a weight of mg newtons acting directly down. The other forces that we've got going on here are the tensions. So we've got a tension here, and we've got a tension there. Now those two tensions are the same, and the reason for that is because we were dealing with a single string. If we were dealing with two separate strings, we would be dealing with two separate tensions, but they're connected by a single string, so the two tensions are equal. Now the job of the tension is to try and keep these two particles together. All right, that's its job, so that they don't get any further apart. So the tension is acting from B towards A, but also from A towards B. Okay. What else do we have? We have the fact that both particles are at a height of 1.28 meters above the ground. We have the fact that on the right-hand side of the pulley here, B is accelerating towards the ground at 1.96 meters per second squared. Now that means that A is also accelerating, but A is accelerating upwards at 1.96 meters per second squared. Those two accelerations are the same. Is there anything else that we can add into this? Doesn't look like it. Now, what I'm not going to do, and this is going to seem a bit strange, is I'm not going to look at the question, because whenever I work with a connected particles question, whenever I work with the majority of mechanics questions actually, I have a set of processes that I apply in any given question. And when I'm dealing with connected particles, I model each particle separately, and I write down the resultant force. Okay. Now, the reason I'm just going to do that without looking at the question is you're going to be asked a variety of things. You might be asked to calculate tension. You might be asked to calculate acceleration. You might be asked to calculate the mass. You know, it's the same stuff over and over again. And effectively, all you're doing is setting up a series of equations to solve. So all I can do without even looking at the question is I'm going to model both particles separately. Okay, now this is just one way of doing this. You can model the whole system as a single equation. I prefer to model them separately. So I'm going to start by modeling particle A, and I'm going to write down all the forces that are acting on A. So we're dealing with Newton's second law, F equals ma, and A is moving up the page, so the tension is going to be a positive value because it's moving in the same direction as the movement. So I'm going to have tension, and then I'm going to subtract the 3g newtons, so the tension up minus the 3g down, is equal to the mass 3 multiplied by the acceleration 1.96. Tidy that up a little bit, t minus 3g, and 3 times 1.96, just go straight to the calculator, 5.88. And that's as far as I can go with particle A. I've written an equation of motion using F equals ma. Next, I'll do the same thing for particle B. F equals ma, and I'm going to write the equation of motion. So this time, the tension is going to be negative because it's acting opposite to the direction of travel, but the mg is going to be positive. So I've got mg minus t, and that's my resultant force, equals the mass m multiplied by the acceleration, which is 1.96. So quite a lot going on in this second equation. I don't know what m is. I don't know what t is. All right. So from equation, I'll call this equation 1 and equation 2. So I've got equation 1 and I've got equation 2. Right. That's the first thing I do. So I'm now going to look and see what the question actually wants me to do. For the period before B reaches the floor, calculate the tension in the string. Well, I can get that from equation 1, because the only unknown in equation 1 is T, the tension. G is 9.8, so we can work it out. So to begin answering the question, I'm going to say T minus 3G equals 5.88. Therefore, T is 5.88 plus 3G, or 3 times 9.8. So my tension comes out as 5.88 plus 3 lots of 9.8 on the calculator, 35.28 newtons. There's my tension for part A. For part B, I'm being asked to calculate the value of M. So to calculate the value of M, I have a second equation of motion where the unknowns are M and T. But since I've worked out T, and remember the tension is the same for particle B as it is for particle A, I could just substitute in. So I can say mg minus the 35.28. That's this equation here, equation 2, equals 1.96 m, 1.96 times m. And then I can just rearrange and solve. All right, so I can say mg minus 1.96 m equals 35.28. Down slightly. M times g minus 1.96, which is 35.28. Remember, g is 9.8. So we get m equals 35.28 divided by whatever 9.8 minus 1.6, 1.96 is, 7.84. So the mass comes out as 35.28 divided by my answer, which is 4.5 kilograms. So we have our tension and we have our mass, part A and part B, done and dusted. Now, like I said at the beginning of the question, it's almost irrelevant what they're asking you to work out here. If you start by creating 2 equations of motion, one for each particle, you will be able to work out through a combination of, it could be simultaneous equations, it could be as simple as this one here where we were able to work out tension straight away, and then substitute tension into the second equation to find mass, which is still solving simultaneously. But you'll always be able to find out your unknowns. Okay, so moving on then. Question C says, calculate the speed with which B strikes the floor. So we can see, we're already told that B is heading down towards the floor. So we can see that B is going to hit the floor, right? How far is it going to travel? It's going to travel this 1.28 meters. So quite a common theme in these questions is for them to throw in a SUVAT section at the end. Now this is a SUVAT section. How do we know it's SUVAT? Our SUVAT equations work when we have a constant acceleration. And we are given a constant acceleration of 1.96 meters squared in the question. So for any SUVAT question, we start by listing what we know and what we don't know. And we work out, or we choose the appropriate formula and we work out our unknowns. So as I just said, for B to hit the floor, the distance it needs to travel, the displacement, is 1.28 meters. The system is released from rest, another key point in the question. So if the system is released from rest, then its initial velocity is 0. Its final velocity is what we're trying to work out. And the acceleration, as we just said, was 1.96 meters per second squared. The time, in this case, is irrelevant. So which equation do we know that links S, U, V, and A? Well, we have V squared equals U squared plus 2AS. Do a quick substitution. V squared equals 0 squared, which is 0, plus 2 times 1.96 for A times 1.28 for S. So V squared works out as 2 times 1.96 times 1.28, 5.0176, and therefore to find V, we square root the answer, and we get 2.24 meters per second. So we know how quickly B is traveling when it hits the floor. So then comes the slightly trickier part. Now we're being asked, determine the greatest height above the floor reached by A. Now that's interesting. And you have to go back to your diagram and really picture what's going on. As B moves down towards the floor, A moves up. Okay, so A is already 1.28 meters above the ground. It will move a further 1.28 meters in order for B to connect with the floor. But then what happens with A is quite interesting. A will continue to travel. Okay, and if you think about it, again, imagine this is a real life experiment. That's what's going to happen to A, isn't it? It's just going to keep going. It's going to reach a maximum height, and then it's going to drop down to where it was. All right. It doesn't just stop dead. It continues to go, and then it's acting under gravity for a short period before it goes up. It goes up, acting under gravity, and comes back down to where it finally rests. So we've got to consider all of those situations. So at the beginning, A is 1.28 meters above the ground. After, or as B hits the floor, A has traveled a further 1.28 meters. Okay, it started 1.28 meters above the ground, and it moved up by 1.28 meters because B moved down by 1.28 meters. And that's a given, all right? So we know that the minimum distance that we have, at least, is going to be this 1.28 doubled, 2.56 meters. Now, 2.56 meters is the height of A when B hits the ground. When B lands. All right? But as I said, A continues to move just for a short period of time. And in order to find out how far it moves, we're going to need to use suvat again. So we'll list our 5 suvats, and we'll work out what it is we're trying to find. So we're trying to find how far A keeps moving after B hits the ground. How high up does it go? So we're trying to work that out. The initial velocity, right? So our initial velocity when B hits the ground is how fast both particles were traveling when B hits the ground. And that value is given as 2.24 meters per second. Okay? Because A and B are connected by this inextensible string. The final velocity of B is the velocity of A when B hits the floor. The final velocity of A, for the part that we're interested in, is going to be 0, because A will then continue to move until it reaches a maximum height. It will then stop instantaneously and come back down again. So we're looking for where this final velocity is 0, where it stops moving in the air. The acceleration for this part is the acceleration due to gravity, minus 9.8 meters per second squared, because the only force acting on A at that point is the minus 9.8. And again, T has become irrelevant for our equation. So again, we'll use V squared equals U squared plus 2AS. This time, V is 0, U is 2.24. And then 2AS, we've got plus 2 times minus 9.8 multiplied by S. We'll work out the numbers that we can. 2.24 squared, as we've seen, is 5.0176. 2 times minus 9.8 is minus 19.6. Oops, not 1.96. And then we rearrange our equation and solve for S. So 19.6S equals 5.0176. So S equals, back to the calculator, 0.256 meters. So what do these numbers mean? Just to go back, A started 1.28 meters above the ground. It then traveled a further 1.28 meters until B hit the ground. Once B hits the ground, A continues to travel for 0.256 meters before it drops back down again. So the greatest height that A reaches above the ground is going to be the 2.56 meters from here, plus the 0.256 meters that it travels after B hits the ground. And we just add those two numbers together to get 2.816 meters. Now, it's just important to say it doesn't remain 2.816 meters above the ground. That's the greatest height that it reaches. It then drops back down, and where it ends up is 2.56 meters above the ground. Okay, but the question asked the greatest height reached by A. So just to recap, connected particles. Two equations of motion, one for each particle. Use those equations of motion to find out your unknown things, tension, acceleration, mass, whatever they may be. And then if you're asked a subsequent question about the movement of either particle, you're going to use SUVAT. In our case, we had two SUVATs. We had one so that we could calculate how fast B was traveling when it hit the ground. And then we had a second one to work out the greatest height of A above the ground. Now, you may not be asked part C. It may just ask you part D. And what you've got to know is you need this 2.24 in order to be working out part D anyway. All right. So if they don't ask you how fast B is traveling when it hits the floor, you must understand that's a piece of information that you need in order to work out the greatest height of A. So that's it. That's the connected particles pulley question. I will upload a question in the chat in just a second that you can have a go at. The answers to the follow-on question are actually, they're given to you. You'll be given the answer at the end of the question, just in a little rectangular box, so you can see it from there. All right, I'll hover around the chat this afternoon, and if anybody wants to add in any questions, then you certainly can. The video will be uploaded in the next few minutes. Thanks, everybody.